Like, are there any questions?
Ask about number 8.
Sure.
It's the great, that's the challenge. The one about maybe
Yeah.
yeah. Can I ask about it?
Yes, you can.
Yeah, how do we?
Oh, how do you do it? Oh, okay. Yeah, let me see. So, right. So it's a bit more precisely when I say filtration. I mean, so it's called the PBW filtration. So it's kind of word length in a sense, right? So B are in G, AB is in F2 of U, and then you have like BA is also in F2 of U. I'm sure you know this, but I'm just giving background and stuff. So in GU, which means sum of FPU over FP minus 1U. Yes, you think of every element as living in some piece, and then you consider it modulo this piece of lower degree. Like, what should I call them? Okay. In fact, we get symmetric algebra. And then a symmetric algebra, so this contains like elements of G itself. And so what is, you see, so a commutative algebra, you want to think of as functions on something. So what is X a function on? It's a function on the dual space. And in general, this is all functions on the dual space. So yeah, then if you have an ideal in U, then your I is an ideal in S. And then you can take, which is now a subset in G star. All right, so yeah, All right, so we've got this deal where we go to the Joule algebra. We take the image of this submodule, that two-sided ideal. And I feel I might have not stated this as generally as I should have. So, for example, L1 of SL2 is V1 of SL2. So certainly this I stated, right? In this case, it's E minus 1 squared. And in general, turns out that the submodule is generated by this vector, okay? Right, so IK is the two-sided ideal. Well, now I'll put a lower guy there, K plus 1. Okay.
In case that one case positive, right?
K, yeah, sorry, K is when right. Okay, so what does this mean? So I'll take G of this element, but it's already homogeneous, so G of that is the same thing. So retains theta to the K plus 1. All right. Let's go back to in particular, this means that on, so this is a subvariety in G star. And we know that this function, this linear function, to that power annihilates it, which implies that equals 0 because it's like it's Null-Stellensatz type thing. And the other key observation is that this ideal is invariant under the action, so you can exponentiate the action of the Lie algebra and consider applying transformations from the group. So you discover that G invariant, so IK actually contains, for all, roots of the same length, let's say. So by the same argument, all of these linear functions, which are linearly independent, annihilate points in this ideal. So it's actually just the origin.
Yes. Sorry, what's your G? What's a G?
What's G? G is like X. G in endomorphisms of V, I suppose. So V itself has finite dimensional graded pieces. So any automorphism given by I'm sorry. So G acts on VKG by like X. V is defined to be the zero product. Yeah.
The above takes the transport vector to some multiple upper long root vectors, so you get a basic.
Yes. Yeah. I realize that, yeah, there might be a lot of stuff that I've kind of omitted. So like, for example, the fact that when you let zero modes act, this gives an action of the Lie algebra. So in particular, x0 is a derivation of, is this true? It's a derivation of all the nth products. I think so. Yeah. x0 a and b is, well, I mean, I should say is commutator of x0 and an. So there's a formula for this. So this I definitely didn't state, but it's a special case of the Borchard's identity. In general, if you put m here, mj xj a m plus n minus j b, which in this case, so indeed, zero products are derivations of all nth products. So yeah, if you exponentiate one of these operators, and you can for x lying in G, so x in G, which is the V1 part, so delta of x is 1, x0 maps v k to vk, and these guys are finite dimensional. So you've got these operators acting on finite dimensional vector spaces, so you can exponentiate them. It's well defined, and because they're derivations of the vertex algebra structure, these exponentiated maps are going to be automorphisms of the vertex algebra structure, and they'll give you an action of some Lie group, which I guess is the adjoint group. Anyway, then you can use those automorphisms and yeah, to transform one of these vectors into another and yeah, conclude. Yeah. Oh, did I not say the G should be simple? Oh no, I'm sorry. I mean, take all of these with a grain of salt. Yeah, let's say simple. So much more interesting. Oh, I mean, that was interesting, but for K admissible, so let's say, for example, G is SL2. So for other types, it gets a lot harder. But for SL2 admissible level, you also know, well, yeah, this is also general, but this NK is also generated by some vector. You can say some things about it. I mean, you know what degree it lives in, and there are even some explicit formulas. Fagan, Malakov, some very complicated formulas for these singular vectors. So it turns out modulo. Do you remember we had these? No, what am I doing? You're working in the Joux quotient, and also going to associated graded. So it kind of essentially looks like this. And then using these explicit formulas, Malakov and Fagan. Oh, maybe, yeah. Oh, is okay. E to the Q. Actually, P and Q have nothing to do with the, yeah, so let's say A and B. Where omega is the Casimir, or rather the image of the Casimir element in S of G. So knowing that this thing equals 0.
What do you write for omega and what?
Huh?
What do you write omega and
E to, so E of SL2 to some power, some integer power. So if I take a point in the variety by K, omega of P, E of P, like to the A, B equals 0. But the 0 set of omega is the nilpotent cone. Yeah, so it's like H. Well, everyone knows what a cone looks like. Right, so if the point P, yeah, if omega vanishes, then the point P is a nilpotent cone. Cool. If not, then E of P vanishes. But if E of P vanishes, then again you use that it's invariant under the group action. So F of P vanishes and H of P vanishes. So actually it's 0, and again you're in the nilpotent cone. So, which is pretty cool. And then Tomiyuki used this and some. Yeah, what did he do?
Equals to the in this case? Or,
I mean,
because you said the 0 set is goes into the nilpotent cone.
I mean, it could be 0, and it would either be 0 or the nilpotent cone. Yeah, and you, so Tomiyuki extended this argument using this sort of semi-infinite reduction functor for other types. And was able to prove the same thing holds in general, but actually for arbitrary type, for admissible levels, this variety lies inside nilpotent cone. But then you have a lot more variety of things that can happen because it could be some non-trivial closure of a nilpotent orbit. Yeah, but in a sense, the base of this is this calculation, and then there's this kind of argument to extend to other types.
You're saying that there is a this special vector, this generator, as a calculated image for all other types as well?
No. Yeah, so we were asking Tomiyuki about this, and he said, yeah, it's been a long time, yeah, trying to proceed the same way for other types. It's very complicated. So there's more indirect argument to get it.
question?
Yeah.
How about super case?
Oh, no idea.
How much you can do in question 8? So
In question 8,
question 8 is just you
that's the same.
can think. But how about G and super case? How about analog?
I don't know. It's a good question, but like at the level of reduced schemes, everything will reduce to even part, right? So I don't. I mean, like thinking geometrically about super stuff is kind of morally the same as thinking scheme theoretically about usual stuff. Like you take care of nilpotents, and things, right? So, and even in the usual case, this scheme here has got some, non-reduced structure. That's a long way to say that. Yeah, I don't know.
How about integral, I mean, non-negative, positive, or non-negative integer case? Can we say anything? No.
For the super case? Yeah, I don't know. I mean, it's a good question. I mean, I guess right. So G star is now some super variety.
No, it doesn't just reduce to the even case. It's not complicated.
But in what sense? So what's the question being asked really, that it doesn't reduce to the even case?
Question 8.
Do question 8. Oh,
Do question 8. Is it true, or if true, is it true? Yeah.
yeah. Well, does anyone know? So I don't know, but does anyone know the formula for singular vector in the integer level case for super? Oh yeah.
But there's no guarantee that that singular vector generates the.
Okay, but what about positive integer case? Like probably OSP1 2, like OSP1 2n is very similar to evenly algebras, right? Other cases, I don't know. Does anyone here know like the analog of this statement? Yeah, that I could believe.
SL21, we already know that if you take positive integer levels, you don't have to combine that.
Sure. Yeah.
So
Yeah.
theory is,
Yeah. All right.
somebody needs to learn super geometry.
Yeah.
Somebody.
Yeah.
This is the associated variety there to the.
Yeah.
So that means that is for K positive is to that C2 combined.
Yeah.
Since the variety is 0, we have the C2 combined for
Yeah.
those cases. So
Yes. Yeah. Yeah. If this variety is zero dimensional, you can deduce that it's C2 cofinite.
Related question to that case then, do we know for super algebras whether that equivalence is C2 cofinite as zero varieties?
I don't know. I'm not really competent to say. My guess would be that yes. Yeah.
We still have the filtration, we can still make the super group,
Yeah.
but I'm not sure what variety means in that case.
Yeah. I mean this. Yeah. I mean normally. Yeah. Like in the classical story, this is usually meant to be the, an affine algebraic set. It's like reduced scheme. But so doing that's not going to tell you really anything about super algebras, right? Or, so yeah, doing super geometry is fundamentally about doing non-reduced stuff. I feel like typically, like the actual odd part in a vertex algebra usually doesn't spoil C2 cofiniteness itself, right? So. Huh?
Yeah, I think it does a lot of horrible things.
No, what I mean is like the even part is already going to be non-C2 cofinite.
I think SL22, the even part is just two SL2s.
And it's not.
There are no levels for which it's C2 cofinite.
Oh, really? How does that work?
It always has in any reduced.
Oh, okay.
I believe that's true.
But I mean, if you have some odd strong generators, then you kind of, I mean, there's only so many -1 products you can take between them. And then once you've exhausted those, you have to start taking -2 products, and then they go into the quotient. So I would have thought so maybe the theorem that C2 cofiniteness implies finite number of irreducibles fails in the super. It's pretty embarrassing this being recorded. It's just talking rubbish here.
It's recording.
Um,
And you might be right. My understanding was that we never, outside of our students, we never have a finite number of irreducibles. Could be wrong.
well, so this is a good question for to.
You know,
I don't know, outside OSP ones.
So what did you say it was?
yes.
SL22.
Yes, actually, no, I think no, PSL 1 and finite number of irreducibles. So I think I'm wrong.
Ah, okay. But you did say this case has infinite.
That's what I believe. Yeah.
Ah.
So, I think that should be wrong because I know I'm wrong for 1.
One is important. One is important.
Significant.
Significant.
So we think it's even part of C2 cofinite. We're asking whether it itself is.
Yeah, sorry. So just when we look at the even line, you measure comes with SL2, but one of them comes with level K and the other one comes with level -K.
Yeah. Okay.
That's
So right. Yeah, it's already the even part. Right.
So the even part.
Yeah, it's a frustrating thing about affine. Affine superalgebras, right? You almost never get positive definite on both parts of the even part, right? So it's like only OSP 1, 2n is good in this way.
Superalgebras are hard. People don't appreciate that.
No, very good. So this guy is non-C2 cofinite, but indeed its even part is already non-C2 cofinite. So it's not a big surprise that it has a lot of representations. Very good. I mean, apart from doing the same thing as in the even case, but just keeping nilpotence.
This would probably tensorials and graphs and multiples to make everything even and then take the associated variety of that.
Oh, okay.
I don't know whether that's the right thing to do. That's the standard.
Okay. I mean, there's super schemes, right? You just take spec of a supercommutative ring. It's just that its reduced variety is the same as the reduced variety of the even part. Well, if I don't know, unless there's any, are there any questions? Does anyone want to do a specific example?
I think question 7 is the most interesting question for me.
Yeah, let's do that.
There are tensor categories, but they might like to do something else. Yeah, this is good for tensor category people. I know that there are any people here.
The tensor category people will have all done that exercise on day 1 of the
exercise 6.
Alan's volunteering to do exercise.
Oh yeah, come on up.
We all heard of that.
I could do 6, unless someone else wants to, and we can do 7 as well. So I'm going to do 7
Me
first.
as a tensor category person would also vote for 7.
Okay.
With the chairs, so you can do it.
Also, I shouldn't say anything, right?
No, no.
I'll keep out of all this stuff.
So 2 hat. Okay, so this -2, of course, is the Joule-Coxeter number of SL2. So it's a P over Q is fourth, but it's here. So let me start with this kind of standard set of simple roots like before, like I did in the lectures. Alpha, the unique positive root of SL2. And here's right. So theta is the same as alpha. Yeah, can I switch this off?
We'll write faster.
There's something. Can I switch off the screen there?
No, there's no way, unfortunately, but I will.
Ah, no. Oh, no, I can just lift the board up. Oh, good. Right, so we got that guy. What else? So the condition talks about lambda plus rho, pairing that with an alpha. So now I should be more careful than I was in the lecture. So by lambda, actually I mean lambda hat and rho hat. Lambda hat means lambda plus k lambda 0. And rho hat means h check lambda 0 plus usual rho. Okay. Yeah, so 2 plus rho is half the sum of the positive roots. So actually, I write fundamental root, fundamental weight, which is 1/2 alpha. Right? So, okay. So this is 2 plus k lambda 0 plus lambda. Okay, and all right. I hear this should be a
plus finite rows.
Oh yeah, thanks. This could be a positive integer. So for alpha I, this equals. So what should I do? I'll write lambda to be b times fundamental weight, right? So now I've got 2b plus. No, sorry, b plus 1.
Yeah.
All right. Fundamental weight pairs with alpha to give 1. Right. So b plus 1. So b has to be greater than or equal to 0. On the other hand, 4/3 lambda 0, b plus 1 omega times the other guy, minus alpha plus 3 delta is minus b plus 1. And now we've got the other pairing, which is 3 delta pairs non-trivially with lambda. So we get 4. And this has to be in greater than 1. So b is less than or equal to, let's see, minus the 3 here. 3, 0, 1, 2, yeah. All right. So we get 3 possible values from b. Now, the next thing that could happen is that the first root in our integral root system above this guy could be here. Okay. And then in that case, we should get this happening, right? I mean, why did it have to go down by 1? Why couldn't it have just been here? You'll find it's because we've fixed the level to have this denominator 3. Yes, you know that, right, this 1, 2, 3. So this guy is also in our delta lambda, right? And so it's negative, must be. Yeah. So you don't have complete freedom to change all the heights arbitrarily. Okay, so plus 1 plus alpha plus delta minus alpha plus 2 delta. If this were 1, then we subtract 1 minus b minus 4/3. I'm sorry. plus 4/3. B could be, yeah, I think B could be minus 4/3, right? Or, and then go up in stage. So 1 minus. I mean, that doesn't feel right, but it seems to be okay. B plus 1, 4/3. 1, 1. It's okay, right? Yeah. From the second line, B plus 1 minus 8/3. So B, sorry, minus, yeah. Huh? Oh, you're right, yeah, thanks. Yeah. Okay, so.
Sorry, but B should be an integer.
Nope, doesn't have to be.
But that's
In this case, so in this case, when the root system was like this,
But if it's not an integer, it cannot be an integer because it's G plus 1 minus B minus 1 plus 4.
yeah,
This is a different thing.
Yeah. Yeah.
yes. Now I'm in a different right. Now I'm analyzing the case.
Disjoint union of admissible ones.
Yeah, yeah. If the root system was this, then the weight would have to be that, or that. If the root system is this, now it'd have to be yeah.
And that exactly shows us what you told us, that in this case it's always the same root system, but the affine part is dilated. Is that what I'm saying?
Well,
It's affine lattice.
yeah. So this root system here.
Still
So the usual root system has that guy, right? And this shrinking by a factor of 3 is an isometry because that direction is isotropic. Yeah.
So if they have this factor of 3 all about candidate root systems, right?
Yeah. No, our candidate root systems. Yeah. So.
Here it's abstractly the same root system, we'll get the same isometries. But we still have to have this. So it's just like translating, in a sense, the origin and choosing different generators for the symbol.
Yeah. Right. I mean, indeed, this set is a Weil group translation of the other one, right? So yeah, translations act by sending these guys up and these guys down simultaneously. Minus 1, so 2, then minus 8/3. That's 6/3. It's 2/3. So B must be less than or equal to 2/3. All right, so those are exactly the cases. So we've got, okay.
With respect to our choosing here, we can't take the standard root system where we take minus theta plus delta and alpha. That's where we can't use that to get another set of.
No, because if
so we have to use this.
yeah, because if exactly, yeah, if delta lambda contained both of these guys, then it would contain everything. So it would be an integral weight. Yeah. Yeah. Yeah, and the kind of the space between consecutive points that appear over any given root is given by this denominator 3. So let me try doing the remaining case a bit differently. Maybe let me not. I probably screwed up. So I was going to say, well, what is the third case? It's you go up 2 here, and on this side you go up 1, right? So you could observe that this is just the reflection, so the Weil group reflection of that system. So what you should get is you take the dot action applied to these weights, and this gives you the weights corresponding to this case. So yeah, let me do that. I think it'll give the right answer. This is alpha applied to. So what are these? So the dot action is reflection in, so there's 0 minus. So it's literally reflection in that point, right? So minus 4/3 is there. Let me change color. Minus 1/3 and 2/3. So these should reflect to, let's see, minus 2/3, minus 5/3, and what's that? Minus 3, minus 6, be minus 9, minus 8/3. Yeah, they should go down the steps of 3. Okay, so we get 9, if I'm right, admissible weights in this case. Now, 3 of them are integrable with respect to the finite SL2, right? The integral weights, dominant integral weights, and all the others are fractional. Oh yeah. Yeah, so those are all the possible simple root systems, I guess is the answer. Yes, like I say, that the over each simple root, if you keep going up, eventually you'll hit something. So here alpha I, eventually you'll hit something which is in the integral root system. Why? Because that's one of the axioms of admissible weight, which is that the rank of the delta lambda has to be the rank of delta. So if any one of the simple roots was kind of missing from this, so suppose for one of the simple roots, nothing above it anywhere lay in delta lambda, then you'd know that the rank of delta lambda had to be at least 1 less than the rank of delta. Okay, so you know that these numbers exist, and they can't really be any bigger than q, because when you increase by q delta, you add an integer onto the pairing of your weight with. Yeah, okay. So in this particular case, you can kind of just proceed systematically. So you say either we're there, in which case 1, 2, 3 downwards. There's another root, and then the negative of that is also going to pair integrally. So 1, 2, 3 upwards. The height here is 1, but then 1, 2, 3 down, or 1, 2, and then 1 down. And then if you go 1 further, then you're up 3 here. 1, 2, 3. But now a new root has appeared in the positive part. So that's going to be the simple root and not this. And then you go 3 down, 3 up. And you've kind of come back around to the start. Okay, so those are the 3 possibilities, and each one gives you a couple of possible weights.
It seems important that we're fixing the positive roots to change that choice. Because if I chose the hyperplane to be this way instead of that way, then this would be good.
Yeah, I mean
that way around would also be a set of simple roots. It would be the viable reflection of the one you had to start with.
Yeah, I mean the notion of admissible is because it's the same idea as dominant integral, right? So it's dominant integral with respect to a choice of positive roots. And if you chose a different hyperplane, you have a different set of positive roots, and then there's the notion of admissible relative to that. Yeah, but it will be a different set of weights. Yeah. Okay. Yeah, and right, something I wanted to comment on this is that. Oh, time's up. Oh well, I'll just comment and then finish. I have no idea why I'm drawing this table like this. These are 0. Let's call them 0, 1, and 2. And then these are these ones that are like -4/3, 2/3, -2/3. So I talked about this Hamiltonian reduction. So as we know, SL2 with F principal goes to modules for Virasoro, right? So we should get some modules for the Virasoro Lie algebra. And in particular, we should get modules. Well, I don't know how many people know this, but there's a so-called minimal model, 3,4. It's also known as the easing model. Okay. And it's known that this has 3 irreducible modules, right? So what happens is these integrable ones all get destroyed by the Hamiltonian reduction. So these guys kind of look like. Yeah. Both, in fact. Yeah, so the minus reduction is the one that is homologically better understood. Plus reduction. Yeah. Yeah, yeah. Yeah, right. Yes, anything which has finite dimensional graded pieces is going to get killed by this minus reduction. But these 6 up here get sent to kind of 3, 4 modules. And remember, I mentioned that there's kind of this W-to-1 thing going on. So you noticed how half of these weights were obtained from the other half by taking the dot action of the Weil group, and the corresponding the 2 weights that correspond under that image, which I guess are 2/3 going to -8/3. Yes, I guess they're like that. So each pair of these goes to one of these modules. So both of them go to the same module under reduction.
You explain that it does not depend on action of Weil group, parameterization of Cauchy. Wait, yeah, right?
So
You explain.
sorry, is there a question? Or?
You explain the principal case, you consider Goldilocks
Yeah.
admission rate, and the character does not depend on choice. Why do you depend?
Yeah. Yeah, and right, and for other nilpotent elements, it gets more complicated because yeah, not every Weil group image of an admissible weight is also admissible. So yeah, this diagram becomes much less easy to understand. Yeah. All right. And so yeah, I guess that's all.
Okay, thanks. Were there questions left?
But still, you didn't give answer because 7 is determined the admission rate, but you give example.
No, I did determine them.
Yeah.
That's just all.
Yeah, these are all. Yeah.
Ah,
For that level, yeah. I think so.
Why is it 6?
The 6. Oh well.
I don't ask how to do, but
Yeah, why is it? Well, I was going to talk about Kasdan-Lustig tensor products, and yeah, I mean there just wasn't any time at all. So, but the point, of course, is you want to. So the important consequence of that. So that statement is saying that tensoring with the module and its dual are adjoint functors, and in general. You can use it to show that tensoring with one of them is an exact functor, and this is very useful. Yeah, so that's the motivation.
Okay, then thanks again.
Yeah.